Our objective is going to be able to describe events as subsets of a sample space and to be able to apply the addition rule. So let's look at this warm-up first. It just simply wants us to explain the difference between numerical and categorical data. So this is something that was in that first section, 6.1. And basically the difference between numerical and categorical data, numerical suggests a number. So this is something that's got to be measurable. It's got to be a measurable quantity that can be associated with a value. Where categorical is something that's not numerical. So it has a value that's maybe more like a name or a label. So we learned that we can take in a frequency table, we can take categorical data and we can calculate frequencies and come up with some numbers that we can calculate some frequencies about. So today we're going to keep looking more into some of this data, and we're first going to get some vocabulary here. The first one is what's called an event. So an event is an activity or an experiment, which is usually represented by a capital letter. So we're going to have some activity, some experiment, and a sample space, which we kind of have a big space for that. Sorry, a sample space is a set of all possible outcomes for an activity or an experiment. So an event can have some sample spaces, some possible outcomes for that event. A smaller set of outcomes from a sample set is called a subset. The complement of a subset is all outcomes in the sample space that are not part of the subset. So this will make a little more sense when we start looking at an example. A subset and its complement make up the entire sample space. And if a subset is represented by A, the complement can be represented by a few different ways. So we could say not A. We could put this little tilde in front of an A, which would also be said not A. Or we could have an A with a little exponent of C. So we can just say the complement of A. So when we're looking for that subset, that complement, we can look at that a few different ways. So we'll try and practice notation that practices those. So let's just practice this new vocabulary for a second. So let's look at a few different events. So remember, an event is an activity or an experiment. So my first event is to flip a coin. So there can be a few different sample spaces that we could look at. So I'm going to label my sample space with a capital letter. And I'm going to put in my curly brackets here what my sample space is going to be. So when I flip a coin, I could either get a heads or a tail. But I can even break this down a little bit more into a smaller set of outcomes. So I know I can get a heads or a tails when I flip a coin, but maybe I look at something a little bit smaller. Maybe I'll call this one B. Maybe I just look at heads, just a little bit smaller set of outcomes. So a possible subset. There could be others, but this is just a possible. So my complement, I'll call this B to that exponent of C. Remember, that's one of my options for complement. To be a complement is a subset of a subset, is all outcomes in the sample space that are not a part of the subset. So my sample space was heads and tails. My subset was just the heads. So my complement has to be everything that was not a part of the subset. So heads was my only, so the tails was the one that was missing. So my complement is everything that wasn't inside. So that would be my tails. Let's look at the next one. The event is to roll a die. So my sample space Well, a normal die would have 6 different sides to it. So we'll just use that one. I know there's other die, but we'll just use that one. So let's think about a possible subset. What if I just wanted to look at the even numbers on my die? So 2, 4, and 6. Here's a possible subset. A subset is just a smaller sample of my sample space. So that means there must be a complement. Well, maybe I'll change that. Let's put a tilde in front of that. Let's call that not E. So not even would be everything else from the sample space that wasn't in my smaller subset. In this case, it would be my odd numbers, 1, 3, and 5. My next event is to pick a digit from 0 to 9. So my sample space, my options here, I'm going to start with 0 and go all the way to 9. So here's my sample space that I can choose from. Now a possible subset. Maybe I look at something, I'll call it N. Maybe I look at 2, 5, 7, and 9. Maybe that's a pattern. Maybe those numbers mean something to me. Maybe it's a part of your phone number. It's just a possible subset. But then we should have a complement to that. I'll use my other notation here, not N. Well, not N, the complement should be everything that wasn't in my smaller subset. So now I have 0 and 1 that need to go in there. 2 was in, 3 and 4 were not. 5 was in there, but not 6. And then we have a 7, but we need the 8. So a complement is everything that wasn't in the subset of our sample space. So hopefully that vocabulary makes a little sense. If not, please let me know and we can try and look at some more examples. But let's look at some more vocabulary. In this next box, we have a definition of what's called a union. So a union is of 2 events, includes all outcomes from each event. So let's look at our events here. We have event A, 0, 2, 4, 6, 8, 10, looks like even numbers. And we have an event B, 0, 5, 10, 15, 20, which looks like multiples of 5. A union of these 2 events includes all of the outcomes. So I'm looking for all possibilities here, all of those outcomes. So we notice a symbol, and we've recognized this from our interval notations, but we're going to use this OR symbol, this kind of upside down U, or I guess it's just a U, and this is called our union symbol. So this is telling me A union B, essentially everything that's in A or B. So this is saying A, what's in A or what's in B. And we'll notice here, they put them in numerical order, but this is all of our even numbers from set A and all of our multiples of 5 from set B. So our union is OR. It's all of the possibilities in this particular situation. So we can look at this as a Venn diagram. If we look at this first circle, we see that there's 2, 4, 6, 8, and 10, and a 0. So this is really representative of group A. Group B must be the second circle. We see our 0, our 5, our 10, 15, and 20, but we notice that there's this section here that they both have in common. So in a Venn diagram, anything that overlaps that they both have in common would go in that overlapping area of those 2 circles. So in this case, this Venn diagram represents a situation of all of these numbers, their union. We also have what's called an intersection. The intersection of 2 events includes only those outcomes that are in both events. So now I still have 2 events, A and B, same 2 events above, but now I want the intersection, what's only in both of them. So I just want what's in common. Well, if I look at my two sets as they're written, I see that there's a 0 in both of them. I see that there's a 10 in both of them. So they do have those two common numbers. So this is referred to as an AND, or we have this intersection symbol, kind of like an upside down U. So we would say in this case, the intersection of A and B. So this is just saying that it needs to be in both. So it needs to be in both A and B. So we can see that from our sets of numbers. We could also look at our Venn diagram again. So we still have A and we still have B, but what we're really paying attention is to that overlapping piece. What do they have in common? So I just want that overlapping piece, what they have in common. So we could maybe see that two ways. So sets of data can be, we're looking for the union, all the possibilities. Maybe we just want the intersection, maybe what they have in common, but not always do they have something in common. So if the two events do not have anything in common, the intersection is called the empty set. So you could write empty set, but you could also symbolize it with these two curly brackets with nothing written in the middle, or kind of a 0 with a slash through it. So if you're asked to find the intersection where two or more have anything in common and they don't have anything in common, then we just say it's the empty set, and we could notate that either way. So let's go ahead and look at some examples. So turn the page. Example 2, we've got this Venn diagram, and we notice the way it's labeled. We're looking at crayons, washable paints. It says that there's 12 of them. I see in my Venn diagram, we've got a circle called primary colors, so yellow, blue, and red. We have American flag colors, blue, red, and white, and I definitely see that there's this overlapping colors, so blue and red are in both the primary colors and the American flag. And then there's all these other colors that are not inside the Venn diagram. They don't fall underneath the primary colors or the American flag colors, but they're still a part of this set of washable paints. So let's start with question A, and to list the sample space. So my sample space, I'll call S for sample space. Put my curly bracket. My sample space is everything. My sample space is all of my possible outcomes. For this case, we've got 12 different colors, and it doesn't matter the order. I'm going to start with green. And then there's violet. I'm kind of starting in that upper right corner. Turquoise. And we have yellow. I'll go to my Venn diagrams. Yellow, blue, and red. And we have white, running out of space. And then we have all those down there at the bottom. So we have brown and peach, black, magenta, and orange. So here's our sample space. All of the possible outcomes for this particular situation. So problem B wants us to list a subset of the primary colors. So maybe I'll call this P for primary. My primary colors, as listed in my Venn diagram, are my yellow, my blue, and my red. So this is just a subset of my sample space, these three colors. List the subset of the American flag colors. So maybe I'll use an A for American flag there. We have still the blue and the red, but we also have white. So let's practice some of our new notation now. Now it wants us to think about P, and remember this upside down U, or this U is our or our union. So this is or. So we have our P, our primary colors, which is our yellow, blue, and red, or our A, our blue, red, or white. So remember, a union is everything. We want all possibilities listed for this. So my set of primary colors or American flag colors, again, it doesn't matter the order. I'll start with yellow. They both have blue and red, but we also need a white. So all possibilities. Now I want to think about my primary colors P and my American flag colors. So and is that intersection. What do they have in common? Where do they overlap each other? So in our Venn diagram, we see that they both have a blue and a red. Problem F, we see that P with a little C in the exponent, which means that's that complement. So we're thinking of all of the outcomes that are not a part of my subset. Now, which subset? Because we had two of them, right? We had our primary colors and our American flag colors. So we'll really notice that this says P, so I'm thinking my primary colors. So everything that's not a primary color. So again, this list is going to be a little bit long. So our primary colors are yellow, blue, and red. So we need to list everything that was American flag except for the blue and red. So that would just be white. And all of these that are outside that weren't part of those two smaller subsets. So a complement of our primary colors, I'm going to start with green. We have green, violet, turquoise. We also have our white from our American flag. And then we have everything at the bottom. We have brown, peach, black, magenta, and orange. So our complement is everything that wasn't included in that original subset. Okay, problem G, we notice that tilde in front, so we know that that really just means not. And then we know that this right in here, this P or A, we've already figured out P or A. So to be in our primary colors or our American flag colors, we did on D, which was yellow, blue, red, and white. So to not be this, which would mean to be its complement, we need everything that's not yellow, blue, red, or white. So again, this could be a little bit bigger list. I'm going to start with that green again. Green, violet, and turquoise. So we don't want it to be yellow, blue, red, or white, which is everything that's inside of those Venn diagrams. So now I'm going to everything that's underneath. So we have brown, peach, black, magenta, and orange. So hopefully after doing those, that vocabulary means a little bit more with some examples there. But again, if you have any questions, please let me know. All right, let's talk about probability. Probability is a value that represents the likelihood that an event will occur. So this is something that you've done before. You know, what's the probability of picking a blue marble out of a bag, or a jack of diamonds out of a stack of cards, or flipping a head or a tails when you do a coin toss. So a probability is just a likelihood that an event will occur. And it can be represented as a fraction, a decimal, which we just want it to be between 0 and 1, or a percentage. A probability of 0 means that an event is impossible. So if we get a 0, it just means it's not possible to happen. And a probability of 1 means that it's going to have to occur. It has to happen. So 1 is the best as far as probability goes. 100% chance that something's going to happen. 0 is no chance. So we say events are independent. Events are independent if the occurrence of one event does not change the possibility or the probability of another event occurring. So we say that we have independent events if we take the probability or the occurrence of one of them and it doesn't change the probability of another event. We say events are dependent if the occurrence of one does actually change the probability of another event occurring. So independent doesn't change each other, but dependent does. So for example, drawing marbles from a bag without replacing it is independent. So if I have red and blue marbles in a bag, if I draw a marble out, regardless of the color that it is, and I put it back in, I have the same probability of drawing that same marble back out. But while drawing marbles with the bag without replacement would then be dependent. So if I drew out a blue marble and I keep it, then my probability has changed for drawing another blue or red out of my bag the next time. So independent doesn't change the probability of the next event occurring, but dependent does. So one last thing, and then we'll look at some examples. We have what's called joint probability. Joint probability. Joint probability is the likelihood of 2 or more events occurring at the same time. So if we have a joint probability, what's the likelihood that they're both going to happen? So we're going to look at several examples dealing with probability. Let's look at this table that's right below it, and let's just think about our formula for figuring this out for a second. So probability is the likelihood that something is going to occur. So you'll see a lot of times capital P for probability, and then a capital A, remember, is how we note an event. So what's the probability of A happening, whatever A happens to be? So we are going to make a relationship. The likelihood of something happening is the number of favorable outcomes, or in other words, what you want to happen. Yeah, what you want to happen is going to be our outcomes over the total number of possible ways. Like, how are the total number of ways that we could do this? So let's look at a quick example, flipping a coin. So the probability of getting heads. So I want heads. Well, the number of favorable outcomes, there's only one head on a coin. But how many total outcomes are there? Well, there's heads and there's tails, so I have 2 different ways that could happen. So the probability of getting a heads is 1 out of 2. Well, let's look at what if we had a joint probability. What's the likelihood of 2 or more events happening at the same time? So we'll see our notation change here a little bit. What's the probability of A and B happening at the same time? That's that joint probability. So we're going to multiply the probability of event A times the probability of event B, So as we look at this, flipping a coin and rolling a die. So what's the probability of getting a heads and a 5? Well, the probability of getting heads is 1 out of 2. There's 1 head out of 2 possible outcomes, head or tail. But on a dice, if I'm going to roll a die, there's only 1 way I can get a 5 out of 6 total sides on a dice. So I end up with 1 out of 12 ways that both a head can be flipped on a coin and I can roll a 5 on a dice. So we have a 1 in 12 chance of something like that happening. Let's turn the page and look at example 3. Let's keep thinking about this joint probability. Find the probability of each event of flipping a coin and rolling a standard die. So as we look at A, the probability of tails and an even on a die. Well, to get a tails, there's 1 out of 2 chances. There's 1 tail and there's a heads and a tails, so 2, times an even on a die. Well, there's 2, 4, 6. There are 3 evens out of 6 total being rolled. You could also think of that as 1/2. 3 out of 6 is 1/2. And we can multiply those together. So we have a 1 in 4 chance of getting a tails and an even number on a dice. Let's look at B. The probability of heads and rolling a 4. So again, heads is the same as tails. We have a 1 in 2 chance. But rolling a 4, there's only 1 4 on a 6-sided dice. So we have a 1 in 12 chance of getting a heads and rolling a 4. Problem C, a heads and a number greater than 3. So again, heads is just 1 out of 2, but to be greater than 3 would be 4, 5, and 6. So again, there's 3 ways out of 6 total, but I'm just going to go ahead and think of that as 1/2, which is really just 1/4 chance. Okay, last one on this. Probability of heads and rolling a 7. Well, heads is definitely 1/2, but hopefully you're already thinking you can't roll a 7 on a dice, which means the probability of that happening is 0. So anything in this case times 0 is going to give me a probability of 0. So if it's not possible to get something, our probability will always be 0. So the last thing we want to look at is what's called the addition rule. And here we have the addition rule. So the addition rule, let's look at it first and then we'll look at an example. So this is said the probability of A or, right, that's our or symbol, that union, A or B. So we would lump everything together, all possibilities. So the probability of an event A or an event B happening. So our rule says we're going to take the probability of A plus the probability of B, which kind of makes sense because if we want all possibilities, we have to add them together. But here's the interesting part. We have to do some subtraction of the probability of A and B. So let's look at an example to understand why we've got to subtract this off. So below we have an example. It says A, a letter in the word algebra. So there's our first set. So we've got algebra, or a letter in the word geometry. So event A is going to be our algebra, and event B is going to be our geometry. So we look in this Venn diagram, and my first kind of bubble here is the letters for algebra, and my second is geometry. So, and in the middle we see that overlapping E, G, and R that are both in algebra as well as in geometry. So if I want to find all of the possibilities, here, starting with my event A. Well, the probability of event A is going to be that 6 out of 26. There are 6 letters in algebra out of 26 total letters in the alphabet. The probability of B. Geometry has 1, 2, 3, 4, 5, 6, 7 letters out of 26. But here's the thing. I counted E, G, and R when I counted algebra, and I also counted it when I did geometry. So there are 3 letters that got counted twice. So that's why we have to do some subtraction. Anything that overlaps, anything that they have in common, we need to subtract off. So this right here is telling me I need to subtract off anything that overlaps. So I'm going to say subtract any that overlap. There were 3 letters out of the 26 that have overlapped and repeated themselves. So when we have a common denominator, we can add and subtract numerators. So 6 plus 7, so 13, minus the 3 gave us 10. 10 over 26, we'll always simplify these ratios if we can. And we end up with the probability of 5/13. So the probability of these two words, algebra and geometry, all the possibilities, there's 5 out of 13. So that's where we're going to stop today. We've kind of gone over a lot of vocabulary, so definitely practice on your assignment. And if you have questions, please let me know. And go ahead and self-assess, and good luck on your assignment.